All right, ladies and gentlemen, welcome back. This is AP Chemistry, Equilibrium Lecture 6.2. Now we're going to get a little bit further into, or more in depth into writing our equilibrium expressions. These are the same learning objectives that we had in 6.1. Essentially, all I need you to do is be able to write equilibrium expressions. We're eventually going to use those to describe the value of that rate constant. And then this is kind of going along with the same thing as 6.1, where you need to understand what the equilibrium expression is telling us and what the equilibrium constant is actually telling us about a particular reaction. All right, so without further ado, here we go. All right, so we're looking at equilibrium expressions, and we kind of discussed this in 6.1, but they're going to be mathematical operations that, and essentially they're going to give us a ratio, and this is important. They'll give us a ratio of product concentrations versus reactant concentrations for a reaction. And so if we're looking at the particular reaction, we've got sulfur trioxide, and it gives us our products here. Notice we do have a balanced chemical equation. You always want to make sure that your reactions are balanced, since, as we saw last time, it's the coefficients that determine the exponents on there. Let's go ahead and write this equilibrium expression for this particular reaction. I'm going to pause it and write mine. You might want to go ahead and pause and write yours and see if you can get it correct here. All right, so here we go. We've got our equilibrium expression. We've got products on top, reactants on bottom, because it's a product versus reactant ratio. And then notice what my coefficients dictated here. You'll see that this particular 2 becomes an exponent in the equilibrium expression. There is no coefficient for oxygen, so that will just be 1. And then my reactants on bottom, I've got this SO3, and it's going to be squared because of the coefficient there. Now, understand, I went ahead and I put this variable here, this Kc, because we're doing this in terms of concentration, and when we look at it, that's what these brackets mean, right? Is that they actually mean we're discussing a concentration here. Our equilibrium expression becomes our Kc, right? Because it's our equilibrium based on concentrations. Another way that you may see this written a lot of the times is we'll have a KEQ, and the EQ is the default for that, is actually saying that this is going to be a concentration-based expression. All right, because what we're going to do is we're going to get into later on in this particular lecture where we look at particular equilibrium expressions that are not based on concentration. So we're going to go ahead and start stating that up front. So you need to understand that the C at the bottom, or a lot of the times the EQ, the Kc means our equilibrium expression is based on concentrations. Okay. So now what we're going to do is we're going to look at the other way that we're going to be writing our equilibrium expressions. And notice it's the same reaction that we had just a second ago on the last particular slide. And then now notice that all of the species in the reaction are actually in gases. They're gaseous states. So if you think back to your pre-AP or your other chemistry classes, I want you to remember Dalton's law of partial pressures. And essentially Dalton's law of partial pressure states that I've got a P total, right, a total pressure, and that's going to equal the pressures of all of the partial pressures of all the gases that I have present, right? And this can go on forever. However many different gases there are, that's how many different partial pressures I would have. Now, it's really important to understand too that essentially I've got, if I had a concentration, it would be equal to the number of moles divided by a volume, right? So I've got a number of moles divided by a volume, and using Dalton's law of partial pressures, we can actually figure out what the number of moles there. So since we can relate the number of moles to a pressure, we can use this in an equilibrium expression because it'll still give us our ratio of our products to our reactants. So what our equilibrium expressions based on gases are going to look like is we'll actually have a Kp expression, and then I would actually write pressure, and then I'm going to go ahead and put the molecule down on the bottom, so it would be SO2. I'm going to put it in parentheses because this is going to be squared. So we're still using the same set of rules to write this stuff. And then I would have the partial pressure of O2. And then I would have that divided by the partial pressure of SO3. And again, I'm going to put this in parentheses because that is going to be squared. So notice it's very, very similar to our equilibrium expression based on concentration, only now we're going to dictate it's a Kp, and we're going to be using pressures rather than concentration. So if you're giving information in pressures, and a lot of the times our units of pressure here are going to be ATM. So you really want to make sure that you're familiar with atmospheres and how to convert to and from atmospheres. And if you're kind of sketchy on that, then let's talk and let's get you reviewed on that. And then I guess that's really it. Other than the fact that in the derivation of this, we are going to end up with Pivnert again. So PV equals nRT, our ideal gas law, will come into play here. And we'll see that here in just a little bit, but it's used in the derivation of all of this stuff. So you might want to also go back and review some of your notes on Pivnert and the ideal gas law. All right, so, here we go. I guess this is where we're going to use it. So we've got our Pivnert, PV equals nRT, and we're going to have this ideal gas law for each of the individual gases that we have in a particular reaction. And if I want you to look at page 659, because I'm not going to go through the derivation here of how they came up with the particular equation that I got shown on the paper, but you're going to want to look at that and kind of be familiar and see how Pivnert relates into this, and so that you don't get lost on some things. But essentially, something that I didn't tell you last time, but Kp, I'm going to go ahead and say that Kp is not necessarily equal to Kc, right? Not always equal is what we're going to put, not always equal. And we can't make that assumption because these are pressures and these are concentrations. They're a little bit different a lot of the time depending on what the situations are. But if you look at the particular equation that we've got here, I've got my equilibrium pressure, my concentration, equilibrium constant, and then I've got RT, and this is the gas law constant. So R is gas law constant. Right? And we're going to use the one for ATM because our pressures are going to be ATM. And then my delta N right here, this is the change in moles in number of moles of gas. And so essentially this is going to be products minus reactants. So the number of moles that are in the products minus the number of moles that are in the reactants, and that's going to be my delta N here. Now, one thing I want you to go ahead and point out is if I end up with a delta N equal to 0, so now I'm down here, my equation, I've got Kp equals Kc and then RT raised to delta N. If my N is actually a 0, so this is a 0 up here, all this stuff goes away. And so at that point, if there's no change in moles of gas, the number of moles of gas from products to reactants, then that's when your Kp is going to equal your Kc, but you've got to be able to look at a chemical equation to figure that out. This is definitely this expression that's going to relate Kp and Kc. It's something that you're going to have to commit to memory. Make sure that you have that equation memorized as you're going through and get used to using it. So hope there's no more questions. If you do have some questions about this, write them down. Ask me some questions when we get back into class, okay? All right, so now what we're going to do is we're going to go ahead and start wrapping this up, but we've got to take a look at heterogeneous equilibria. And so not always are all of my species all in the same state of matter. So the examples that we were looking at early on here, everything was in a gas state. But what we're going to do is we're going to take a look at what happens when they're not. So I've got a gas, and now I've got a solid. And the real question is what do we do with solids and liquids in these equilibrium expressions? Because the concentrations actually don't change during a reaction, right? If I've got a solid piece of carbon, the concentration of carbon in that solid is the same. It doesn't change because if I get some of that carbon that reacts and goes away or is formed, then my volume change is proportional to the amount that's there. And so the concentration of solids and liquids, they're actually constant. They will not change. And so what we do is we actually, to compensate for that, because we don't want it messing up our equilibrium expressions, is we exclude them. Since they don't change their concentrations, we will exclude them from our equilibrium expressions. And so if I'm looking here at my example, right, I've got a Kc expression written right here, an equilibrium expression based on concentration. I would have carbon monoxide down on the bottom. It would be squared, just like we would expect. And then I would have my my products up on top. Well, I've got CO2 and carbon. But the question is since this is a solid, do I write it in my equilibrium expression? And the answer is no. So I would get rid of that. My equilibrium expression would just be CO2 over carbon monoxide squared. All right, so we will not write them in our equilibrium expressions. And then real quick, I also want to point out that I could write a Kp expression for this, right? Since what I'm going to put in my expression is actually gases. And so this would look like it would be the partial pressure of CO2 divided by the partial pressure of carbon monoxide squared. And again, I would leave the carbon out because it's a solid. All right, and so in this particular case, since I've got gases in my expression, I can write a Kp or a Kc, whichever I want. Now, if you have any kind of aqueous solvents in your chemical equations, you can't write a Kp expression, and we'll see that here on the next page. So let's take a look at that. All right, and before we do that, I guess really what we're going to do is we're going to look at liquids as well, and we need to understand at the same time, just like solids, the concentration of a liquid doesn't change. As long as we have some liquid present, it's going to be the same concentration, whether we have, 50 milliliters of it or 500 milliliters of it. So like, for example, my water, which is what's going to appear most often, 5 milliliters of water and 100 milliliters of water, it's the same concentration. Right, and so again, we're going to leave those out of our equilibrium expressions. So notice my CO2 down here on the bottom, my hydrogen and my hydrogen carbonate, both of those are in my equilibrium expressions, but I leave my liquid, my pure substances, out of my equilibrium expressions. All right, and for this, the question that I'm going to leave you with here is, could I write a Kp? Could I write a Kp expression for this reaction since I have a gas? And the answer is no. And the answer is no because I've got aqueous substances in my reaction. So my Kp cannot have aqueous. All right. So I actually would not be able to write a Kp expression for this reaction because of that. All right, if I'm going to use a Kp expression, everything in the expression has to be a gas. Okay, so for this one, we would only be able to write a Kc expression. So hopefully that sheds some lights on how you're going to be able to write these expressions. And go ahead and write down any questions that you have and start on your practice problems. And I'll see you in class.